Hey there, welcome back to Short Takes 331. Today we're going to talk about the basics of complex numbers. So complex numbers are numbers of the form z equals x plus iy, and here x and y are real numbers and I is the imaginary unit, and it's such that I squared is -1. If this looks a little weird, it's because, well, it sort of is. People had to come up with this kind of object to find the roots of all algebraic equations. So basically the roots of all polynomials. For us, this is really going to be more an interest towards quantum mechanics, and we'll come back to that in a couple of videos. For now, we call this x the real part of z and this y the imaginary part of z. Notice that this y doesn't include the I. It's often a point of confusion among students. When asked about the imaginary part of a number, they try to put this whole thing into that imaginary part. It's just the y, not the I. So the imaginary part of a complex number is itself a real number. We can represent this complex number into a plane like this, the complex plane. And so we would use normally the horizontal axis for the real part and the vertical axis for the imaginary part. A given complex number x0 plus iy0, we can call that z0, would then look like this. It would be some point on the plane, and then x0 would be the projection on the x-axis and y0 the projection onto the y-axis. And of course there will be this kind of hypotenuse here where whose length would be x0 squared plus y0 squared square root, as you would expect. And of course there will be an angle and so on. And we'll come back to that in just a bit when we talk about the polar representation. Now, for now, suppose we have two of these complex numbers, z1 and z2, with real and imaginary parts x1 plus iy1 and x2 plus iy2. So real part, imaginary part, real part, imaginary part. And if you add them, if you add these two complex numbers, that's a basic operation you for sure want to have. You simply add the real parts with the real parts and the imaginary parts with the imaginary parts. So this is activity here. So x1 plus x2 and y1 plus y2 as the imaginary part. For the product, it's a little bit more complicated, but not much more. You just take these two numbers and you multiply them, and you have to take into account, of course, that I squared is -1. And so when you do that, you'll find that the result of multiplying z1 with z2 gives you x1, x2 minus y1, y2. This minus definitely comes from this multiplication of I with I. And then you have an imaginary part that is the cross terms, basically x1, y2 plus x2, y1. As always in mathematics, addition and multiplication are fine, but when you want to divide stuff, then is when you have to get more creative. Things get more complicated there. And so the division of z1 by z2, how do you do it if you have an I there? Well, the way to do it is to introduce something called complex conjugation. So suppose you multiply and divide by something we call z2 star, which is exactly equal to z2, except that we flip this plus sign for a minus sign. So we change the sign of the imaginary part. And if you do that, you can see that z2 star is simply x2 squared plus y squared. We'll come back to that below. And then the top is z1, z2 star. And so you can multiply these two numbers, z1 plus z2 star, by using this definition of z2 star. And so that gives us this top part, x1, x2 plus y1, y2. Notice the sign difference here and here. This is the real part now. And then the imaginary part is, once again, the cross terms, but again, there's a flip in the sign. So you have y1, x2, sort of like here, but you have minus x1, y2. So it's the minus relative to the multiplication side. And so then you divide by x2 squared plus y2 squared. So this x2 plus y2 squared is, of course, just the magnitude squared of z2. And so let's talk a little bit more about that. So when we complex conjugate a number, when we flip the sign of the imaginary part, we obtain this thing we call z star. So we get x minus iy if our complex number was x plus iy. And if you multiply z star by z, you get this result. You get a product of the difference and by the sum of these two numbers. And so it's the difference of the squares, as you would expect. And so you obtain x squared minus the iy squared. And so this is x squared minus iy squared. X squared is the same, and y quantity squared is minus y squared, which with this minus sign cancels the sign, and you get x squared plus y squared. In other words, a complex number times its conjugate gives you the magnitude square of the complex number. And this is why we use that up here, why we use this multiplication and division by z2 complex conjugate to carry out the division by z2. So that gives us the advantage that then the whole denominator now is a real quantity, and we know how to divide by a real number. So that's no problem, and that's why we introduced this complex conjugation. But it's an operation that appears in many places in physics, especially having to do with time reversal and complex conjugation, and charge conjugation, and so on. We'll get back to that hopefully in a future lecture. Before that, let's talk about this polar representation of a complex number. So a complex number can be written, as we saw before, as a real part and an imaginary part, and we saw that in the complex plane. And of course, like we said, there's a magnitude and there's an angle, and so that's what gives you the polar representation. So it's going to be a radius, if you want, or a magnitude of the complex number, and an angle associated with that relative to the x-axis. This is usually how this angle is measured. And so then we will have a real part, which is simply the x component, which is r cosine theta, as you would normally have in geometry in 2D. And then you have an imaginary part, which is given by the y component, which is of course given by r times the sine of theta. So the length of this side of our triangle is simply given by r sine theta, and so that's the imaginary part. And so this gives us the polar representation. Another way to write this polar representation is using the so-called Euler formula, or Euler's formula, which tells us that e to the I phi is cosine phi plus I sine phi. And we'll prove this in our next video. But for now, this allows us to combine this expression that has two terms into a very compact formula that is simply r times e to the I theta. This is really what we call our polar representation of complex numbers, and it's extremely useful and extremely compact. More specifically, this r is, as you know, x squared plus y squared square root, and then this theta is the arctangent of y divided by x. This is exactly as you would expect from two-dimensional geometry. To give you an example of why this is useful and powerful, notice that z to the n can be written as r to the n, using the left-hand side here, times cosine theta plus I sine theta to the power n. So this is here taking the r as a common factor and then multiplying by cosine theta plus I sine theta. And so everything to the power n just gives me this. On the other side of the equation, I can elevate that to the nth power as well, and I get r to the n times e to the I n theta. And now, using Euler's formula, this n theta becomes the argument of the cosine and the argument of the sine. And so this gives us some relationships between the cosines that would appear from elevating this to the nth power and the cosine and the sine of n times the angle. And so let's take a look at that. How do we expand this mess here? Well, we use the binomial theorem. So we go ahead and take the fact that this is just two terms elevated to the nth power, and we use the famous Newton binomial theorem, where we have a sum from p equals 0 to n of the binomial coefficient n k, and then we have the cosine to the kth power, and then I sine to the n minus k power. You could expand this, for example, for n equals to 2 and see what happens, for n equals to 3 and see what happens. And when you equate both sides, and you look at the real part and the imaginary part of the result, you obtain formulas for the cosine of n theta and the sine of n theta in terms of the cosine theta and the sine of theta. So for n equals to 2, it's a very simple example. You can take the square here of this and put n equal to 2 in this formula. And of course, the r to the n cancels. I didn't mention that, but of course it does. And so you would obtain from there that the cosine of 2 theta is just cosine squared minus sine squared of theta. So it's just from this squared plus this squared, and the I gives you the minus 1 here. And then on the other hand, you have the cross terms, which give you the imaginary parts, as we saw before when you square. And here the imaginary part is just sine of 2 theta, and so you obtain this second formula here. So this is very useful, very powerful. It's a very simple way to obtain formulas for the cosine of 2 theta, 3 theta, 4 theta, and so on and so forth. And you can do that to your heart's content on a rainy day. So more interesting than that, and all those algebraic questions, is considering functions of a complex variable. And this may be something that you may not have seen before. So usually introductions to complex numbers sort of stop here and maybe prove some theorems. But it's interesting to consider sort of the analysis side of the story. So how do we define complex functions of a complex variable? Well, you would have a complex plane in your domain, of course, and you would have a complex plane of your image. And so our function f of z will be a function of x and y in this combination, z, x plus iy, and you would obtain w as a result, some number that lives in this other plane, where there's a real and an imaginary part. In other words, f of z can be written as some some real part, which is a function of both x and y, and some imaginary part that is a function also of x and y. And usually those are called u and v. Now, this is all very nice. We just imagine that there is such a mapping between two complex planes. Can we differentiate this f of z with respect to z? What would that mean? How do we do integrals? What about Taylor expansions? And what about the whole of calculus? Can we generalize that to complex numbers? And the answer to that is yes. A lot of it can be generalized, and it becomes extremely interesting and actually very, very useful. So let's start with derivatives. So we go ahead and try to generalize our definition of derivative by simply considering this limit. Suppose that this limit exists. We can take this limit as delta z, a small change in z in the complex plane, goes to 0 of this ratio, f of z plus delta z minus f of z divided by delta z. And if that limit exists, we should be able to take it as delta z goes along the real direction or along the imaginary direction. So we take the limit in a horizontal way. We can take the limit in a vertical way in the complex plane. And if the limit exists, we must obtain the same result here where this question mark appears. And that gives us these conditions called the Cauchy-Riemann equations. So it turns out that if such a limit exists, then it must be that the derivative of the real part and the imaginary part are related in the following way. So the derivative of u with respect to x must be equal to the derivative of v with respect to y, and the derivative of u with respect to y is minus the derivative of v with respect to x. These conditions are necessary if this limit exists, but they're not sufficient for this limit to exist and for us to say that f is a differentiable function. But if f is a differentiable function, if this limit exists, then the Cauchy-Riemann equations are satisfied. And we'll come back to this in a future video as well. Now, generally speaking, from the operational perspective, I just want to get the message across here that derivatives work pretty much as you would expect. So the derivative of a monomial z to the n is of course n z to the n minus 1, as you would expect. The derivative of the sine of z is the cosine of z. The derivative of the cosine of z is minus the sine of z. All that is exactly as you would expect as it works with real numbers. And of course, the derivative of the exponential is just the exponential and nothing else. And in the same way, series expansion of all these objects work as you would expect. So every case that is well behaved and with real numbers and doesn't have any issues works pretty much in the same way for complex numbers. You do have to be careful, however, with quantities or with functions like the log of z or fractional powers of z. Those that are always a little weird with real numbers also get a little weird with complex numbers, and you have to be more careful. And we'll come back to that in future videos. So here's a very, very simple example. F of z equals z squared plus 1. And in fact, this is sort of one of those cases for which complex numbers were invented. If you try to find the roots of this, the numbers for which this vanishes, you would obtain that z has to be I, and so, or minus I, and so that its squared gives you minus 1, and so this vanishes. So this polynomial, z squared plus 1, has roots only in the complex plane, but not on the real axis. Now, coming back to our interest in derivatives, if you want to take the derivative, you go ahead and you differentiate just as you would for the real case. You have df dz is simply 2z, and this 1 goes away, and that's all there is as far as the derivative. If we write it more explicitly, this function in terms of its real and imaginary parts, we find that u of xy is just x squared minus y squared plus 1. That's just from squaring this and then adding the 1. And then the imaginary part is just 2xy. So it's the cross term that appears when squaring that, and this is just v of xy. And you can see right away that du dx is simply 2x. It comes from this, and it happens to be exactly equal to dv dy. And then du dy is minus 2y, which is of course exactly equal to minus dv dx. And so the Cauchy-Riemann conditions are satisfied, and so everything is consistent, and that we obtain exactly what we thought we would obtain. That is to say that this very simple function is differentiable. The limit of the ratio of the differences as described here exists, and it exists no matter how you take that limit, and the result is simply, in the general case, given by 2z, and it satisfies then the Cauchy-Riemann conditions as expected. And that's it. That's all I have for this very quick and basic introduction to the basics of complex numbers. If you enjoyed this video, please like and subscribe. And as always, if you need a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comments section below. And I will see you next time.